us. First up, on the very first one, is Peter Hurst. Peter's a nationally recognized biochar expert, and here at SimSoil, we've been learning a lot about biochar and how it can be used both for soil health and for stimulating the reproduction of soil microbes by creating an optimal environment for the microbes to live. Peter has a new title. We're calling him the Director of New Co-Product Development. And Peter, why don't you start by talking about what co-products are?
Co-products, in my view, are those products that we make either in combination with other people's products, such as biochar, or which naturally fall out of the production of the products that we make and that our supplier makes. So I'm not taking credit for our flagship product, SimSoil. That belongs to Elizabeth and especially to our chief scientist, Katie. But my realm is looking at the different combinations of the things we do make as components of SimSoil and the finished product of SimSoil and combining them with various other things that are out there, particularly biochar, which is what brought me to SimSoil. For those of you who already know something about biochar, forgive me, because I'm really starting from square one. And for those of you who have only recently heard or maybe even never heard about biochar, this should pretty much start with at the beginning and bring you through to the state of the art of biochar, at least as concerns SimSoil and is most exciting to me here at SimSoil. This were 10 years ago. I could pretty much sum up the world of biochar in the amount of time we have. But so much has happened in biochar, I can barely introduce you to one penguin standing alone on the tip of the iceberg. So rather than try to give you a very broad overview of what biochar is and where it's going, I'm going to pick out certain selected features of it, which should do two things: give you some idea of the power and value of biochar, and in this session, give you some hint of why it is such a powerful, if small, nonetheless powerful component of what we're doing here at SimSoil. So let's get going. We call it a new old technology because in fact it's thousands of years old, was discovered by Western civilization, so-called, in South America about 450 years ago, and then promptly forgotten. It turns out it was responsible for the agricultural flourishing of the civilizations in Mesoamerica up until the time of European exposure and the decimation of those civilizations, and sort of lay dormant for 400 years till it was rediscovered in the late 1980s and very slowly gained recognition and prominence. And we'll get to more detail about those discoveries in a little bit. But let's start with what biochar is. It is essentially charcoal, but it's a very special type of charcoal. And you can see from this slide that IBI, which is the International Biochar Initiative, has been struggling with the definition of it for some years and has some descriptors of it, which are not really a definition because it's not readily capable of being separated from other forms of charcoal by any clear line, but it is produced at higher temperature than the charcoal you may be familiar with. It is cleaner in the sense that most of the tars and oils and flavors that make charcoal grilling so delicious have been burned off, or more accurately, pyrolyzed off, leaving as much pure carbon as possible. This is what it looks like in application. We have bags and bags of material that looks just like this in our yard and at a storage facility. And it comes to us in this raw form. And this is pretty much the raw granulated form that it comes right out of the producer's biochar reactor, received here on site and goes into our blends. This is one of the classic illustrations, still available on the IBI website and many, many other places, which for years and years has illustrated the power of biochar in the Terra Preta soils, that is dark earth soils of South America, where it was first discovered. Now you can see this is 4 pictures, not 2. The farmer is not standing over a cutaway of his own soil, but this illustrates the type of soil that each of these corn crops is growing in. On the left is typical tropical soil, which, as you can see from its color, has very, very little organic content of any kind. Most of the biomass and most of the organic matter in a tropical rainforest is up in the canopy, not down in the soil. And corresponding to that is the type of crop that could normally be grown in Amazon soils in the absence of treatment with biochar. On the right, you see the same farmer on his biochar test plot with a cutaway of the type of soil just below him. And yes, that is a 2-meter measuring stick below him. Some of these Terra Preta soils ran 6 feet deep. And the color of this soil, which we will come back to later, is not a direct result of the fact that it's got a little black carbon in it. The color of this soil corresponds to what you see in the color of any good, dark, rich soil. It's full of humates, full of organic matter, which has, in this picture, progressed down to a depth of 6 feet. And this is soil that has not been touched for 400 years, since the civilizations that built the soil disappeared. In order to understand why this soil produces the kind of crop response you see here, it's sort of necessary to understand what goes into it. So let's start with a little chemistry. This is a diagram of lignin, which is the most important component of woody material. It's very closely related to cellulose and hemicellulose, and in fact, it's sort of the glue that holds the cellulose and hemicellulose together, gives it strength, sort of like the resin in a fiberglass car body or boat body. And as you can see, you see the little hexagonal shapes that look like nuts that fell off of a bolt somewhere. Those are all benzene rings, or molecules of 6 atoms of carbon, forming a very complex matrix held together with more carbon, more hydrogen, and more oxygen, which is what makes up lignin. It's a big carbohydrate, in effect. It's a big complicated sugar. Well, when this material is heated up to a certain temperature in the absence of oxygen, it doesn't burn, but all these bonds you see represented by the straight lines, not by the hexagonals, but by the straight lines, they all pop apart, releasing the hydrogen and the oxygen, and leaving most of the carbon in place to form a much tighter matrix of mostly carbon benzene rings. This is called amorphous graphene. Picture a very, very thin sheet, 1 or 2 or 3 atoms thick, that behaves sort of like aluminum foil. When you crumple it up, it maintains all that surface area, but becomes a very small, tight, compact mass of mostly carbon chains, mostly carbon bonds here, but you can also see there's a little bit of oxygen left, there's a little bit of hydrogen left, and those are some of the things which distinguish biochar from activated carbon, for instance, which is almost pure carbon, and give it some of its active qualities in soil. So if you take a flat sheet of this honeycomb and crumple it up, you get what we call amorphous graphene. You can see at the bottom right hand, this is that scale is 10 millionths of a meter. So this is an electron scanning microscope view of amorphous graphene, and you can see the positive spaces filled by the material and the negative spaces in there. Those spaces you're looking at are the home for just about any of the very, very smallest soil microbes there are. And water molecules down to sheets of water, also 1 or 2 molecules thick. This material is left in the woody material that it comes from in a structure that reflects the actual microscopic structure of the wood. What you're looking at here is the actual vascular structure of plant material, which stays in place. When biochar comes out of some reactors in big chunks, you can actually see the wood grain left in the surface. And that structure persists all the way down to the microscopic and even nanoscopic level. The first magical thing about biochar is that all this surface attracts microbes and it attracts organic material and builds up a skin or a crust or a varnish, which when it's aged looks like this. And as you can see, it's a very, very bumpy surface at the same scale of 10 micrometers, and creates even more surface area for other exchanges to take place on. And it's this organic coating on the microsurfaces of the biochar where the magic occurs, the increase in cation exchange, which is the most important chemical process in the soil for nutrient exchanges between plants and the soil microbes. Some of the benefits that this results in is soil structure, plant health, enhanced root growth, nutrient filtration, an establishment of seed coatings, microbe carriers. We'll get to another quote here in a minute, which I think sums all of this up quite nicely. But you will hear a lot about biochar production of energy, which is, again, what we call a co-product. And you'll hear about it sequestering carbon. And in fact, a lot of presentations will lead with those two, as if those are the main reasons to use and promote biochar. And I don't think they do, and neither does Johannes Lehmann, who's the world's leading scientist on biochar. He actually puts carbon sequestration a distant third behind agronomic benefits and energy production. And the reason for that is he's done very careful studies, very close analysis and economic analysis of the value of increasing soil health for its own value, and finds that on an economic and environmental level is even more important than carbon sequestration. Another way I look to put it is that if you're really producing good biochar, you're taking care of the soil. And to paraphrase Lewis Carroll, if you take care of the soil, the sea will take care of itself. We don't have to make any extra effort or go to any extra cost to sequester carbon using biochar. It does it automatically.